Hello, good evening, everyone. Welcome to One Concept, Multiple Tools, Multiple Learnings. I think this is my 13th video on this particular web series. And today's topic of interest would be on rotation. I think we have still in the unit A, we have rotation and as well as relativity theory. So today we'll be doing with rotation. Okay, let me share my screen to start with this. So as you know, in the chapter on rotation, so we have something like very basic things. Of course, you don't need any sort of what you call simulation to work with, but still, as a sake of completion, I would like to show this one here. But of course, there are certain things which you need to know while we discuss about rotation. So as a result of it, I am doing this. Okay, the first one is about understanding rotational motion. So this is from the site here. I'll be putting the URL there. The first one shows you that if you click on this particular button and then click on this, so as you see, the time keeps on going and initially the rotation starts, and as a result of it, after some time, you observe that the rotation becomes faster and faster. So what can we say about this motion? We can say that there is an acceleration over here. Okay, so this is only to show what do you mean by an acceleration. How do you calculate the acceleration? In fact, you cannot calculate the acceleration. You will be able to show, so what is angular acceleration? Let me click on any one of the other motions over here. Let me stop here. Let me stop this, reset this. Let me start with this. So here also it starts from rest, and let us look at what's happening to the velocity of the motion. Angular velocity is seen to be increasing faster and faster. So there is also an acceleration here. We can also discuss about what is the angular acceleration and what is the angle, what is the direction of the angular acceleration. You can use using your finger rule. Okay, right hand thumb rule. Since it has been moving like this, you can say it has been towards the screen, right? Okay, let me stop it over here, and then let me click on this one here. Now, what's the difference between this motion and this motion? The first motion, it was going in a clockwise direction. Second motion is going in an anti-clockwise direction. Once again, there's an acceleration only. There is no deceleration. Okay, there's a rotational acceleration or angular acceleration. There's no deceleration. Don't take this acceleration to be negative and say this is angular deceleration. No. Okay, fine, because only the angular speed is seen to be increasing. So therefore, you should not take that. Let me click on this. Play here. It's moving at some angular velocity. Is it changing? It is not seen to be changing, which means it is moving with a constant angular velocity. The angular acceleration in this case should be 0, right? So this is how one can understand about the different types of angular acceleration or maybe deceleration, what's happening. We can get to know about this. This is also an angular acceleration, but this value would be negative. Sorry, this would be positive and the clockwise direction would be negative over there. Okay, and then let us click on this. Right. Now again, there is no change in the velocity. So this is also constant angular velocity. Angular acceleration is 0 here. Yeah. Okay. Linear acceleration is there, but angular acceleration is 0 here. Okay. Now let me go on to the next one. Now this shows you about the differences between angular velocity and angular displacement. So as a result of it, there are two bees as you see over here. One is a beetle, other one is a bug over here. You can keep it at any distance. You can pull it across here. Let me keep it over here. And then what I can do is I can keep it over here, for example. Keep this one here. And then I can measure the distances over here. From here, I can measure the distances. I can say there's 1 centimeter. Sorry. It is like this. Initially, you can keep it like this and just give the answer as, for example, this is 1, this is 2, this is 3, and ask what was the error in this. You can say the error is because this is systematic error. I had not kept it at 0. Okay, I kept it at a different division. So I should actually keep it at this point. Right. So these kinds of questions can also be addressed using this. And you say this 1, 2, 2.5. And here, like this, you can find out. And then what you can do is you can click on the go here. Okay, so you can go click on the go here and see, find out. Okay, so what is the angular velocity of the disk? So angular velocity of the disk can be computed from here, and it is shown in the graph also here. There's a red color and a green color over here, which has been oscillating like this. If you look at this, the amplitudes of this red and green are different, while the time at which it crosses the center is the same, which means the time period is same, while the velocities and the amplitudes can be different. As we move away from the center, the amplitudes will be larger. As we move closer to the center, the amplitudes will become smaller. So you can tell all these things over here. Okay, and you can calculate what is the linear velocity, rotational velocity, how do you calculate all these things, you can easily find out from here. Let me go on to the next one. This is about angular acceleration. So in an angular acceleration setup, what you have is you have something like a pulley, and then the other one end of it is fixed over here. To the other end, you see there's a mass which is being hung through a string, and then you can vary the masses over here. You can take 0.1, 0.2, 0.3, and so on. And this platter is nothing but a pulley that we have. It will have a number of turns over here, and then the spindle radius. This is a spindle radius over here. You can increase the radius, you can decrease the radius. For example, in this case, I kept it at 0.01 meter. I can keep it at 0.03 meter also. Much larger over here. This radius is larger. Let me for example keep it at 0.01 here. Let me make 3 platters over here. That means the string has to rotate like this, and then this 0.1 kg. And now what we do is, let me click on the acceleration. If I play this, but first let me reset this. Now I have set all this value, and then I can find out what's the value of theta, what is the value of omega. Omega is angular velocity, alpha is nothing but angular acceleration. Let me click on this. Now notice what's happening over here. The object is seen to be falling down, right? It's slowly falling down. It has to rotate through 3 turns of it, and as a result of it fall down. And look at the value of alpha. Alpha is not changing. What's omega? Angular velocity. Angular velocity is changing. What's the value of theta? The angular displacement. Okay, one turn is 360 degrees or 2 pi radians. And if it keeps on moving something like how many ever rotations it goes, you find out, multiply that by number of rotations. 2 pi multiplied by number of rotations will give you this value, right? So therefore, you can find out the angular velocity, you can find out the alpha, everything is seen to be a constant. Now, let us ask the question whether if I change any of these parameters, does any of these parameters change, especially the alpha value, does it change? Okay, let me take it as 1 platter, for example. Let me reset this, keep it 1 platter, and keep this as 0.02 meter spindle radius, and let me click this. The alpha value change, right? So we do not know for what value does it change. Does it change because of the number of platters, or is it changing because of spindle radius? So what you should do is, you should actually change only one at a time. Okay, if you know the math behind it, then it's fine. Else you have to change only one at a time and thereby get an answer for this. Okay, let me move on to the next. This is about a rolling motion. So wherein you have an object which is seen to be rolling like this, okay, along an inclined motion, because inclined plane, because of the gravity which is pulling it like this. Okay, there are several objects which one can use it over here. The kinetic energy is initially shown over here. The mass, radius, inclined angle, everything can be changed. Let us take the default values and then run it across to see what happens. When I click here, you see all the 4 objects are being sent together, and then you see this sphere reaches first, the wheel reaches last. Now, what could be the reason behind it? We can ask this one. That means the time of sliding, time of rolling from one end to the other end, the distance being constant. Why does the wheel go slowly? Why does the sphere go faster? Okay, this is something one can ask. If the same force has been given, so what depends on it, right? So does it depend upon the moment of inertia? Does it depend upon the mass of the object or radius of the object? So we can get to know more about this. We can ask the students to go through this one and get an answer behind this. Move on to the next one. So all this is physics, very simple simulations that we have. Okay, next is, right, angular momentum. So what is angular momentum? Moment of momentum, which is nothing but MVR. MVR is nothing but angular momentum, or I into omega is angular momentum, right? So towards it, you see the radius of the cylinder is given over here. The radius of the person's path, where this is standing over here. See, he's standing at the periphery over here, at the edge over here, because you see the 1.75 meter and this 1.75 meters. Okay, so it's at the edge. Maybe if I increase the radius of the cylinder, now what do you observe? The person is standing at the middle over here. So not middle, very nearby to the center, right? The mass of the person is given, mass of cylinder is given. I can find out what's the value of omega. Omega is seen to be 1.72 radians per second. The centripetal force is seen to be 344.2 Newton. If I reduce this value, radius of the cylinder, if I reduce it, now what's happening? Centripetal force is higher and the value of omega is also 3.65, right? Earlier, what was it? It was 1.72. When I come here, it's becoming faster. When I come very nearby to it, it becomes much more faster. If I still go here at 2, it's very fast over here. Now let us ask the question, what happens if it goes less than 1.75? Is it possible, first of all? Now I went to 1.45. Okay. Now what's happening here? The person's path also changed automatically. The reason is because if I make this 1.75, that means the person is standing at the edge. If I reduce this much further, that means the person is outside, right? He is no more being active and is not being rotating along with the cylinder. So therefore, okay, that is something which it makes. You can ask these questions to find out, okay, what is the minimum value? Why should it change? All these things, which gives us a lot of critical thinking. Okay, next. Let me move. Now, this is a worksheet that we have on rotational dynamics, which is based on the previous simulations that we have seen so far. Okay, you can use the same simulations. You can ask the students, give this as an FA, and ask the students to work on it and try to get the answer. See, the same one, right? So you need not prepare any questions. So directly we can ask the student to do with this, and finally it becomes easy for us to correct. Next. This is something like you have a sphere and then you have the radius. You can change mass, you can change. This sphere appears to be very similar to what we have seen here, right? We had seen the same sphere here also. Okay, it went off over here. Okay, but anyway, but this experiment is different over here. There it was an inclined plane. Here it is, you are dropping an object over here. Let me reset this. See, this is what it is. You have kept a solid sphere over here. The mass of the sphere is 5 kg, radius is 1.5 meter. You are pulling downwards with a force of 20 Newton. And as a result of it, we are finding out the torque over here. Okay, let me click on this. We are finding out the torque over here, which is 30 Newton meter. And how does this torque change and what is the value of alpha? How does it change based on all this? Okay, inside of an gravity which is acting on an incline, now there is a gravity which is acting downward like this, right? You can get this to know about it. Now let us say I reset this and I increase the mass and I decrease the mass to this much. I make a smaller sphere. Okay, and I click on this once again. Now what do you think will happen? This is smooth, so definitely it moves much more fast. The value of alpha has increased from 6.67 to 12.5, right? If I increase this, 12.5 becomes now what? What becomes to 12.5? Let us see that it becomes 5 over here. That means as the mass increases, the angular acceleration starts decreasing, right? You can get to know about it. Now, in a similar way, you can also use a spherical shell or maybe a solid cylinder or maybe a cylindrical shell. Then when you start this, for this earlier you got 5. Now let us see what's the value of alpha you get. You get 2 over here, right? That means the speed, the pickup speed that this rotates is much, much slower. Now you can ask the question, if that is the case, why do we need a circular wheel for an automobile to run? Okay, if the pickup speed is very slow, why can't I use something like a sphere, right? So get the answers from them and see how does it work with. Share your answers if you get anything like this. Next. This is quite interesting. Let me just reset all of them. Reset it. It has a trace also. Now what you show here is that, see, there is a coefficient of friction here. Now initially I make this friction to be 0. Okay. And I keep the solid cylinder over here and I run this. So what do you expect? What's happening to the cylinder? Cylinder is sliding over here. It's not rotating, right? Now what I do is I increase this friction. I increase this friction to 0.09. Okay, very low friction. Now let me run this once again. Now it starts moving. Initially it is sliding and the path that you see here is nothing but one of the points, okay, on which it starts sliding, moving over here or rolling over here. See, this is the region where it is slowly sliding and at the same time moving, right? Now what I will do is let me increase this friction to a much more larger value. That means at this point itself it started to move, right? It started to roll. Which means friction is very essential for an object to rotate. Without friction, it will only slide. Now, this value differs from one object to other object. And you see, because of the friction, there's a loss in thermal energy also. There's a loss in energy which accounts for the thermal energy. Now, let us say, for example, instead of this one, if I create a solid sphere. Now, where does it start rolling? It starts rolling from here itself over here, right? Starts rolling from here itself. If I use a thin cylindrical shell, now you see, it slides for a moment and after that only it starts rolling over here, which means it needs a lot amount of friction, right? Then thin spherical shell, you see, it still needs a very large amount of friction and after that only it will start rolling. Okay, if this friction is 0.38, it will not roll immediately. It takes some more time to roll across and then only it will do it. So like this, you can get to know about it. Okay, how does the friction plays a role over here in rolling? Let me move on to the next. There are some more examples over here from the O Physics website. You can look into it. I'm not looking into each and everything. Of course, this is quite interesting. Rotating disk. Okay, this is nothing but rotation with collision, or maybe you can say it's an inelastic collision. Okay, now how does it work? Angular momentum person on a rotating frame. Let me run this. Initially, top cylinder has a height of 2 meters, radius 5 meter, omega I minus 10 meter. Okay, minus 10, which means what? It's moving in the one direction, opposite direction, or maybe in the clockwise direction. Bottom cylinder has a height of 1 meter, much smaller because it's 2 meters, it's 1 meter. The radius is 8 meter, much larger one, and omega I is equal to plus 5. Here it was minus 10, it's plus 5 over here, and the mass is 64, and here mass is 50. So this will be able to tolerate that weight. Now let me click on show numbers, and then what I'll do is I'll do this run over here. Now what's happening? One is rotating like this, other one is rotating in the opposite direction. So it's rotating like this over here. After some time, what happens? So this comes in contact, and then the moment it's dropped, after some time it comes in contact, and then it starts rotating with the same angular velocity. Okay, it's also same angular velocity. Anything else that we have to show here? Okay, here it shows about what is the top cylinder's mass, what is the bottom cylinder's mass. Everything has been shown. What I will do is I will, I have kept the friction between this to be 0.5. This is what needs to be investigated. Instead of 0.5, if I make this friction to be very, very small, I keep it like this. Okay. Now let us investigate. I'm not changing anything else. I'm just running this and see what happens. What's happening? After some time, it starts moving. Let me make this to be equal to 0. I can't make 0. It's 0.1 is the minimum. If it was 0, it would be much more interesting. Okay, you should ask this question, what will happen if it becomes 0? Now you see, this is rotating like this. This also rotates for a while longer than what was expected. And then it goes along with it. Because what happens is friction tries to minimize that rotation over here. If there's no friction, the upper disk would have been rotated in a clockwise direction, and the lower disk would have rotated in an anti-clockwise direction. This will continue to move on. Okay, but unfortunately, there is a friction. So it tries to coerce it, or it tries to pull it across and try to rotate in the same angular velocity. Okay, so we have seen all the simulations, which are very basic, and but anyway, it helps a student to understand more about rotation. You can also give this to students and ask them to work on this. With this, I think we have done with the chapter on the rotation. Rotation, we don't have much over here. Those are very simple simulations, but anyway, it's of use. Thank you for being with me. So do like, share, and subscribe to my channel for more updates. Thank you.